Okay, class, we're starting on real-world parametric equation problems this week, specifically mostly sports problems. And the following is a real-world example, and we're going to create out of that real-world example in the video clip a parametric equation problem, and we're going to use the parametric equations to analyze what is happening to the flight of a ball that's being thrown 300 something feet in the air to home plate from the outfield. So I hope we'll learn how to set up these equations and insert them in the calculator and then analyze to see the maximum height of the ball, the time it takes the ball to get to its final destination, and the distance covered horizontally by that ball before it or when it hits the ground or some such thing. So that should be pretty helpful for what we're going to be doing the following 2 weeks. So here is the video now.
They're voting for the All-Star in the outfield. Still one of the starters. Bautista taking over.
And he rips that one down the left field line. Cespedes on the move. He's not going to get it. And it rolls off the side wall, and they're going to wave home Kendrick. The throw to the plate is there.
Oh, my goodness.
They got him. Are you kidding me?
Wow.
Cespedes did not pick it up cleanly, and when he finally did, he threw it all the way in the air, and Kendrick was out at the plate. And Scioscia's out to argue.
Now, ball goes off his glove, and then he kind of hesitated. He was getting ready to throw and then realized, I've got to throw. And you talk about a throw. They're going to look at the play. And quick throw. And if he doesn't drop the ball, it's going to be second and third. But it's there, and it's the first base umpire making the call. But an unbelievable throw all the way in the air. And I guess they can look at a couple of things. Did Derek Norris put his foot down and block? Or did he tag him right there? And if you got the upper leg, the bottom leg wasn't on the plate. So that's perhaps what they were looking at. But if he's out, that's the most remarkable throw and out you'll ever see.
Here's the verbal description of the video you just saw. On June 10th, 2014, Oakland A's outfielder Yoenis Cespedes from Cube threw out Angels baseman Howie Kendrick, attempting to score home plate. His throw was clocked at 132 feet per second, an angle of elevation of 17 degrees from horizontal. I'm going to go ahead and show you what that looks like and make a little sketch here below. So what you have, if you look at this XY coordinate plane, the throw leaves the outfielder's hand at 6 feet above ground and goes in this direction like this, all the way to the ground like this. And this angle here, I'm going to draw this little dotted line. This angle from horizontal is 17 degrees. This is angle of incidence or angle of elevation. Okay, so that's just the setup. Units are in feet, okay, 6 feet above ground. And we're interested in three things: how long a throw it was horizontally. So we have is a distance here, horizontal distance. We want to know the height, maximum height of the ball, which is going to be this one right here, h. And we want to have the time it takes for this throw. And so the throw is going in this direction with time. So how do we write an equation for that? Well, a parametric equation is one in terms of x equals and y equals. And what is x going to be equal to? So position versus time. Well, the initial velocity of the throw is 132 feet per second. And what do we multiply this by to get the horizontal component of 17 degrees? Well, it's going to be cosine of 17 degrees times t. And so we can input t and figure out how far horizontally that throw is. And y equals, we start out, we talk about elevation. We are starting out at this height of 6 feet above ground. So we have 6 plus, and what do you expect to have here? 132 times, what is the vertical component here? Sine 17 degrees T. Now if we have just these two terms here, we're going to have this throw continuing to go in this direction all the way into outer space. But what is going to happen here? The throw is going to be going toward the ground, so we have minus 16t squared, accounting for the influence of gravity. So now we can go to our calculator to do our analysis. So we get to our calculator here, and we go to y equals, and the first thing we notice is that we are in a function, we're not in parametric mode. So to get to parametric mode, we go to mode, and we come down here to the fifth line and go over to parametric, press enter. And now we can go to graph, and we don't see anything. Of course, we got to go in here, and we put 132 cosine 17 and t, and we have y equals 6 plus 132 sine 17 degrees t minus 16 t squared. Okay, so if that's it, we go ahead and graph, and we get this looking thing here. It doesn't look anything like a throw. Well, let's go to our window, see what we see here. We go from 0 to 6.2, and we go by this. Do you see anything that's amiss here? There is really something that is amiss. What happens is that we are in radians, and the 17 we have here are in degrees. So we got to go back to mode, and we're going to change this radians to degrees. So we change that to degrees, and we go ahead and graph now, and now this is what we look like. Okay, so at 6 feet the ball is going up in this direction. That looks better. But now let's go to the window and get everything outlined. Now we do these parametric equation sports problems. The t minimum is set at 0, and t maximum is usually set as standard at 6.28, which is 2 pi. And that happens to work for most sports problems. A ball in the air on this earth is not going to be up for longer than 6.28 seconds, unless it's a bullet or some ballistic implement like that. And then for t-step, which is the amount of time, I recommend going to 0.01. And 0.01 represents what? 1/100th of a second. Now it's going to mean we're going to be scrolling a long time, but that's going to be helpful to us to get to a more exact resolution when we get to the critical points. Okay, X maximum, we're going to go to 350 feet. If you looked in the video there, as you had a wall that was, I think, 347 feet in the background, and we're going to go with possible maximum height of 50 feet. And we'll see what, when we graph this, looks like. So we can see the entire path of the ball. So we're interested in the distance from the y-axis all the way out to the x-intercept here, the height of the ball, and the amount of time it takes. And we'll go to trace, and we can go to the right. Now, you notice that we're advancing t by 0.01 at a time, which the con is it takes a long time to scroll to where we want to, but the pro is that we get a very exact resolution. And so what we're looking for is the maximum y value, or height. So we get there, we see 29.23, 0.25, 0.26, 0.27, 0.27, 0.2. So we're looking about 29.27, which can be about 29.3 feet. So I'm going to go over here, and that's going to be question 2. Maximum height, 29.3 feet. Okay, now we can just continue scrolling to answer the rest of our questions. So we continue scrolling to the right, and what we're looking for is for y getting to 0, or as close to 0 as possible. So we keep on scrolling to the right, and the x value is the horizontal distance from the outfielder, and the t value is the time it takes, and the y value is the height in feet above ground. So we get height of 1.6, 1.22, 0.8, 0.37, now negative 0.05. We go back here. So as close as we can get to 0 is this going to be negative 0.05. And so x is 323 feet away, and time is 2.56 seconds. So that's going to be problem 1, 323 feet to outfielder's hand to home plate, and 3 will be 2.56 seconds. So that's it. Now I hope you're able to follow along in your calculator, and you're going to have an opportunity these next couple weeks, I hope, to work out a lot of these problems, and I hope this is helpful. Good luck, and thanks for viewing.